We have made antimatter, not in theory, not in a thought experiment, in a laboratory, on Earth, right now. At CERN in Switzerland, machines are producing antiprotons and positrons in measurable quantities. Every hospital with a PET scanner uses antimatter annihilation to image tumors. The International Space Station has an instrument measuring cosmic antimatter from space. Antimatter is real. We have it. And we cannot store it. The most energy-dense substance physically possible, annihilating 1 gram of antimatter with 1 gram of matter, releases the equivalent energy of a 43 kiloton nuclear weapon. And we cannot keep a microgram of it for more than minutes. The storage problem is not an engineering obstacle we're close to solving. It's a constraint written directly into the physics of what antimatter is. I should know. I'm the one who predicted it. In 1928, I was 26 years old, trying to write a quantum mechanical equation for the electron that was consistent with special relativity. The mathematics forced something I didn't expect, solutions with negative energy. Mathematically, the equation required particles with the same mass as the electron, but opposite charge. Mirror particles that nobody had seen. The obvious response was to throw those solutions away as mathematical artifacts, unphysical. I didn't. I followed the mathematics. Carl Anderson found the positron, the anti-electron, in a cloud chamber in 1932, 4 years after my prediction. The mathematics was right. Antimatter was real. Let me tell you precisely what antimatter is, because the popular picture is almost always wrong. Antimatter is not negative matter. It doesn't repel gravity. We'll get to that. It's not some exotic alien substance with strange properties. It's a mirror. Every particle of matter has a corresponding antiparticle with identical mass and opposite charge and quantum numbers. The positron has the same mass as the electron, exactly the same, but positive charge instead of negative. The antiproton has the same mass as the proton, but negative charge. They're mirrors, not opposites. And when a particle meets its antiparticle, both are completely annihilated, not damaged, not changed into something else, gone. The entire mass of both particles converts into energy, gamma rays mostly, plus some other particles depending on what's annihilating. Einstein's E equals mc squared in its most literal, most complete form. Every kilogram of mass, if annihilated with an equal kilogram of antimatter, releases 1.8 times 10 of the 79 joules of energy. The Hiroshima bomb released about 6 times 10 of the 13 joules. The math is straightforward and the numbers are staggering. So why can't we store it? Here's the problem. And it's actually very simple once you see it. Every container you could possibly build is made of matter. Any wall, any surface, any material the antimatter touches is matter. And antimatter touching matter means annihilation, instant, complete, uncontrollable. You cannot put antimatter in a glass bottle. You cannot put it in a steel container. You cannot put it in anything physical, because anything physical is matter. The solution we currently use, don't let it touch anything. Suspend it in a vacuum, held in place by magnetic fields. A penning trap uses electric and magnetic fields to confine charged antiparticles, positrons, antiprotons, in the center of a vacuum chamber, orbiting in electromagnetic fields, never touching the walls. This works for individual particles or small clusters, for minutes or hours at most. Any power interruption, any field fluctuation, any vibration that nudges the particles towards the walls, annihilation. The trap cannot scale. CERN's alpha experiment set the current record by holding a few hundred antihydrogen atoms for about 1,000 seconds in 2011. That's 17 minutes for a few hundred atoms. We need grams. We can hold nanograms, briefly. That gap is not a minor engineering problem. It's a reflection of how fundamentally incompatible antimatter is with the material world. Now, before we get to why this matters for the future of physics and space travel, let me tell you about the application that's already running that almost nobody connects to antimatter. PET scanning, positron emission tomography. If you've ever had a PET scan or known someone who has, you've encountered antimatter annihilation. Here's how it works. A radioactive tracer is injected into a patient. As it decays, it emits positrons. Those positrons travel a few millimeters through body tissue before encountering an electron. Annihilation. The two particles convert into a pair of gamma rays traveling in exactly opposite directions at exactly 511 keV each, the energy equivalent of an electron or positron at rest. The scanner detects those gamma ray pairs. Because they travel in opposite directions, the detector can triangulate the source to within millimeters. The annihilation event is the imaging signal. The physics of antimatter annihilation, applied to medicine, gives us one of the most precise biological imaging technologies that exists. Every time a cancer is detected early by PET scan, antimatter physics is what made it possible. I find that worth noting. NASA's applications are different in character. The Alpha Magnetic Spectrometer on the International Space Station measures cosmic ray particles, including positrons and antiprotons coming from space. This is fundamental research, studying where cosmic antimatter comes from. Are there large-scale antimatter structures in the universe? Are the positron excesses we measure from distant sources signs of dark matter annihilation? These are open questions being investigated right now. The energy and propulsion implications of antimatter, if storage were possible, would be transformative. Matter-antimatter annihilation has a specific impulse, a measure of propulsive efficiency, orders of magnitude beyond any chemical rocket. NASA-funded studies concluded that milligrams of antimatter could get a spacecraft to Mars in 45 days. Grams could enable missions to nearby stars within a human lifetime. Grams. We currently produce about 10 nanograms of antiprotons per year worldwide. The gap between current production and what propulsion applications would require is roughly a factor of 1 million in production and a factor of many millions in storage. I'm not saying this to dismiss the idea. I'm saying it to be precise about where the frontier actually is. And the production problem is, in some ways, more fundamental than the storage problem. We make antimatter by slamming protons together at near light speed in particle accelerators. The collision energy is so high that matter-antimatter pairs spontaneously create from the kinetic energy, E equals mc squared, running in reverse. Energy becoming mass. The annihilation process and the creation process are the same physics, running in opposite directions. The efficiency is catastrophic. Producing 1 gram of antimatter requires roughly 25 million billion joules of energy. At current electricity prices, that's somewhere around $62 trillion per gram. The entire annual electricity production of the United States could produce about 50 milligrams. And here's the deeper issue. Even with perfect efficiency, even if you could capture every antiparticle produced and store it perfectly, you still put more energy in than you get out. Antimatter cannot be an energy source. The annihilation releases energy, yes, but making the antimatter costs more energy than you get back. It's a carrier. An extraordinarily powerful, extraordinarily dense energy carrier. The most energy-dense storage medium physically possible, but not a source. Think of it as the ultimate battery, one that stores energy with perfect efficiency and releases it as pure radiation. The problem is, it costs more energy to charge than you ever recover. That doesn't make it useless. It makes it a technology problem of enormous difficulty, not a physics impossibility. Now I want to tell you about the deepest problem that antimatter reveals, the one that I find most unsettling. The Big Bang should have produced equal amounts of matter and antimatter. The physics that creates particles creates them in pairs, one particle, one antiparticle, always. If the universe began in a symmetric state, it should have produced equal quantities of both. They should have found each other, annihilated, every particle of matter pairing with every antiparticle and converting to radiation. The universe should have no matter at all, just photons, cooling forever in an empty, expanding space. We exist, therefore this didn't happen. For every billion antimatter particles created, there was one extra matter particle, one that had no antiparticle to meet. When the annihilation was complete, that small excess was all that remained. Every atom in your body, every star, every galaxy, the residue of a process that was almost perfectly symmetric, but not quite. This asymmetry has a name, CP violation. It refers to a slight difference in how the laws of physics treat matter versus antimatter under certain transformations. We've measured it. It exists in particle physics processes. The standard model of particle physics predicts a small amount of it. The amount predicted is nowhere near enough to explain our universe. The measured CP violation in the standard model falls short by many orders of magnitude. There has to be additional CP violation, additional asymmetry between matter and antimatter that we haven't found yet. Some process or processes in the early universe that tilted the scales by just enough to leave a residue of matter. We don't know what it is. This is the most important open question in physics that is directly connected to antimatter. Why does the universe have matter in it? We exist because of a physical asymmetry we cannot fully account for. That's not a satisfying position. It's an honest one. Current experiments are pushing at this. CERN's alpha experiments are measuring the spectrum of antihydrogen, the frequencies of light it absorbs and emits, with increasing precision. Quantum mechanics predicts that antihydrogen and hydrogen should have identical spectra. Any deviation would signal physics beyond the standard model, new asymmetry, a hint toward the missing CP violation. So far, the spectra match. The search continues. In 2023, CERN's alpha-G experiment measured whether antihydrogen falls up or down in Earth's gravitational field. There was a theoretical possibility that antimatter gravitationally repels matter, which would have been a dramatic result, one proposed explanation for the matter-antimatter asymmetry. The result? Antihydrogen falls downward. Gravity treats antimatter the same as matter. That particular explanation is ruled out. The question of the asymmetry remains open. The next generation of experiments will push antihydrogen spectroscopy to parts per trillion precision, probe CP violation in particles containing heavy quarks, and continue the search for the missing asymmetry that explains our existence. I want to close with where this began, with an equation. In 1928, the constraint was simple. Write a quantum mechanical equation for the electron that's consistent with special relativity. The mathematics forced solutions I didn't initially want, mirror particles, negative energy states, implications that seemed like artifacts. I could have discarded them. Physicists often discard mathematically valid solutions if they don't correspond to known physical objects. I followed the mathematics, not because I was certain it was right, because the constraints of the theory required it, and I had no principled reason to throw it away. Antimatter was found. The equation was right. The lesson I carry from that: the universe doesn't ask our permission before deciding what exists. Mathematics, if it correctly encodes the constraints of reality, tells you what must be true. My discomfort with the negative energy solutions was irrelevant. Reality didn't care about my comfort. The matter-antimatter asymmetry is the same kind of problem. The universe exists. That's the observation. The physics we have doesn't fully explain it. Either there's a flaw in our physics, or there's additional physics we haven't found yet. Given that the standard model has been extraordinarily successful at everything it's been tested on, the more likely answer is that there's something missing. Something that, when found, will feel as inevitable as antimatter felt once Anderson photographed that positron track. The most expensive substance on Earth, the mirror image of everything we're made of, predicted by an equation, confirmed by experiment, used in hospitals, studied in space, impossible to store, implicated in the deepest question about why anything exists. The physics was right in 1928. The physics is right now. The part we haven't figured out yet, that's not a limitation. That's where the work is.